Hey everyone, this is Dr. C. In this pre-lecture, I'd like to talk about the Arrhenius equation. So let's just get started here. Grab a pen. All right, so what we're going to right now is starting to look at other factors that affect the rate of the reaction. We've looked at the rate law. How does concentration affect the rate? The Arrhenius equation has the rate constant K, and we know that rate is proportional to the rate constant. So we can interchangeably say that these things in this equation impact the rate. If they impact the rate constant, they impact the rate as well. And there's a number of things here in this equation that you should see. Temperature. Temperature, we raise the temperature, molecules will collide more often, they'll collide with more energy, that will increase the rate. Activation energy, the smaller that energy barrier, in general, the faster the rate. The larger the energy barrier, the slower the rate. And then there's this term A, which is called the frequency factor. And let me scroll down just a little bit here. Okay, A is the frequency factor. It's related to the collision frequency. There's also something called the orientation factor in there as well. Okay, so not only must molecules collide, they must collide with enough energy, the activation energy, and in a lot of cases they have to collide with the correct orientation. All right, so that orientation and the collision frequency are together in this frequency factor. So this one relatively simple equation, okay, puts together a lot of different factors that affect the rate constant and hence the rate. Temperature, activation energy, collision frequency, orientation factor. Okay, and you'll notice the gas constant is in here. We're talking about motions of molecules, collisions, things like that. It shouldn't surprise you the gas constant is in there. One thing to watch out for, this is activation energy, E sub A. We need the gas constant with units of energy. So it's not the 0.0821 ideal gas constant that you're probably most familiar with. It's the gas constant in units of joules per mole, okay, 8.314. I will give you that constant. So this is the Arrhenius equation. Lots of stuff packed into one pretty small equation, but a lot of different factors that affect the rate of reaction. Now, and I knew it was going to happen. I swear I didn't hit anything, and something opened up on my computer. Go figure. It wouldn't be a pre-lecture if that didn't happen. All right, sorry about that. So we're actually going to want to use more often a couple of different forms of the Arrhenius equation. Okay, we won't use that first form. I showed that because that's kind of the simple form, the place to start that has everything in it. A more useful form is one that has the form of a linear equation. Okay, so to get there, what we're going to do is we're going to take the natural log of both sides of the equation. So look at your calculator and make sure you know where your natural log key is. You're going to need that for some calculations. So we take the natural log of both sides. On this side of the equation, we're going to have ln of A, and then we're going to take ln of e to the minus ea over rt, so this part of the equation. We can add those together, and we're not going to go through the math of why you can do that. Okay? So that's on this right side of the equation. ln of e to the x, let's call that whole thing x, is just x. So if we had natural log of e to the x, that just equals x. So we end up getting this minus ea over rt term from that. Okay? And we rearrange it a little bit more, and we end up with this. And I'm going to write it so that I can write it a little bit better than what's here, hopefully. Minus ea over r times 1 over the temperature. Remember, capital T is temperature, not time. Natural log of A. Okay, so there's another form of the Arrhenius equation. You see all the same stuff, right? You see rate constant, you see activation energy, you see the gas constant, you see temperature, you see the frequency factor. This has the form of a linear equation. Y equals mx plus b. Okay, so why is that useful? Well, we can plot some data. Yay! We like to plot data, right? So we can, like on a quiz or exam, yeah, I'm not going to have you break out the graph paper and plot data. But you might have to do it in a homework problem. you might be given a plot and say, from this plot, figure out the activation energy. And how are we going to do that? Well, we're going to make a plot. We're going to plot y versus x. Y is ln k. X is 1 over the temperature. We're going to make a plot. Oh, you're kidding me. Really? Where is that coming from? Sorry, I hate to get frustrated. Happens sometimes. All right. We're going to plot y versus x, natural log of k versus 1 over t. If we've collected good data, we should get a straight line, and we can get the activation energy from the slope of that line. The activation energy from the slope of that line, because the slope will equal to minus EA over R. Then we just have a quick calculation to do. All right, so let's look at a plot. So here's some data. What you would do is you would change the temperature for a known reaction, and then you would determine the rate constant at those different temperatures. Remember, the rate constant is a constant for a given reaction at a given temperature. If we change the temperature, the rate goes up, and hence the rate constant goes up. So we've run this reaction at 5 different temperatures. We've determined 5 different rate constants. Now we're going to plot that data. This is the most frustrating thing I have ever seen. I have no idea where this program is coming from. I have no idea what I'm hitting. So, natural log of k versus 1 over t. Remember the equation. I will give you this equation on a quiz or an exam, but become familiar with this. EA over R, 1 over t, plus ln of A. Okay? So, here's our y, natural log of k. Here's our x, 1 over temperature. Our slope will be minus EA over R. And if we wanted our frequency factor, we could look at the y-intercept. We typically don't need that. Okay? But here we are calculating the slope, delta y over delta x. That slope will equal to minus EA over R. Now, so once we get that slope, we still have to multiply the slope by the gas constant, change the sign, and then we can solve for E sub A. So that's one way that we can solve for the activation energy, okay, from a plot of data. So make sure you know how to do that. We'll do that. You'll have a problem like that in the pre-lecture quiz. We'll do a problem like that in class. And then there's another form of the equation that we will use. And we'll use this one because we'll plot data, but this is maybe a nicer equation in the sense that we only need 2 temperatures, 2 rate constants, and we can get the information that we need. So essentially what we've done is we've taken this equation, same equation, okay, at 2 different temperatures. So we have T1 with a rate constant at that temperature. We take a second temperature where we're going to have a different rate constant. Okay, so a new temperature, let's call that T2. Okay, and then we're going to divide one by the other. And I'm not going to go through the derivation in this pre-lecture, but we divide one equation by the other, and you can see it all shows up here, right? Our 2 different rate constants, natural log term is still there. Our minus EA over R is still here. We have our 2 different temperatures. There you go. So essentially, rather than having to plot a series of data to figure out the energy of activation, we can plug in 2 different temperatures in Kelvin. All right. Plug in our gas constant, plug in our 2 rate constants, solve for the energy of activation. Okay. That's what we'll use this equation more often for, and that's what you'll see in the pre-lecture quiz. You'll be given 2 different temperatures, 2 different rate constants, solve for the energy of activation. Okay, you'll see that. Realize, though, we could solve for something else in this equation. Not going to do it in the pre-lecture quiz, but you could have the energy of activation, 2 different temperatures, 1 of the rate constants, and solve for a new rate constant at that different temperature. Okay? Or you might have 2 different rate constants, 1 temperature, solve for the temperature of the other rate constant. So there's more things we can solve for. In general, we'll use this equation to solve for E sub A. Okay? So Couple of things. Let me just sum up this pre-lecture. Know what the Arrhenius equation is really doing for us, just in general terms. It's really relating many factors that impact the rate of reaction. Temperature, activation energy, collision frequency. We're going to talk more about orientation of collision. All of these are combined into one simple equation. What we're then going to do with this equation, we're going to modify it to make it easier in most cases to solve for activation energy. Again, we can do that two ways. We can take the linear form of the Arrhenius equation, plot y versus x. The slope is equal to minus EA over R. You need to know that. And then we can solve for activation energy. This last thing we talked about is we're actually taking that linear form of the equation at two different temperatures, combining it into one equation. So if we know two different temperatures, two different rate constants, we can again solve for the activation energy. Okay, you'll see a few problems in a pre-lecture quiz. That's all I want to do. We'll work more of these in class, but I wanted to get you thinking about this. I'll test your knowledge on this in the pre-lecture quiz. I'll test your knowledge again in class to reinforce this, and then we will move on to some new stuff. Arrhenius equation is pretty cool. It packs a lot of punch for a pretty simple equation. And make sure you know where the natural log key is on your calculator. You will, in some problems you're going to come across, well, this one you'll have to take natural log of K2 over K1. We're going to talk about using the e to the x key on your calculator in class, which you might have to do on occasion. Okay, I will see you soon. Take care.